All right, so today we are going to start discussing entropy. What is entropy? Okay. Now, the reason I will be discussing what is entropy in the context of the theory of probability is that my experience as a student with entropy, which is probably also your experience, is that typically you introduce entropy in thermodynamics and you have absolutely no idea what it means, in a sense. I mean, you hardly understand what it is there for. Then comes this formula written down by Boltzmann, which connects the thermodynamic entropy to statistical mechanics, to the number of configurations that the system can have, and so on and so forth. That is, of course, a brilliant formula, and it's quite surprising that Boltzmann invented it so early. But it's also, not easy to understand it unless you have some previous knowledge of probability theory. While in the context of probability, entropy is actually something that is very, very simple to understand. So that's what I would like to explain now, entropy in the context of probability theory, and you will see that it's not something so obscure in that context as it is in the context of physics. So what is entropy? Entropy is essentially a measure of the information that is contained in a probability distribution. Okay? So let me make an example. Suppose that, an example of probability distribution. Suppose that we have the following system that has three possible colors: red, green, and yellow. You can hardly see this yellow, so let's put something dark around it. So there is a physical system that has these three colors, which is a traffic light and nothing else. A traffic light. So now, suppose that you go around with your car in Trieste today, right? So you will have a certain probability when you encounter a traffic light of finding red. You will have a certain other probability of finding green, and then a tiny probability of finding yellow. So let's assign some probabilities. I don't know. P red equal to 2/5, P green equal to 2/5, and P yellow equal to 1/5. Okay? Let's say, right? Now, when you find yellow, what do you have to do when you find yellow?
Slow down.
You have to slow down if you're before the traffic light, or if you're already passing the traffic light, you have to, remove yourself from the junction as fast as possible, not too fast, but you have to go, right? So it has some information, yellow, right? It tells you something, that you have to do something. Now, suppose that you make the following experiment. You travel through Trieste at 2 a.m. tonight, okay? So if you travel through Trieste or through any city in Italy, practically, at night, you will see that all the traffic lights are essentially off. And what happens when a traffic light is off? You don't know. You've never seen an off traffic light in Trieste. Well, what happens when a traffic light is off in Trieste is that you see a blinking yellow light. Okay? It's exactly as the yellow light that you see during the day when it's yellow, but it's continuous. You see just yellow, 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 yellow. So overnight, so this is during the day, overnight, you have the probability of red is equal to 0, the probability of green is equal to 0, and the probability of yellow is equal to 1. Now, if you see yellow overnight, what is the information you get? There's no information. It's as if the traffic light was not there, right? I mean, so there is absolutely no information. Because you have absolute certainty of finding yellow, and when you have absolute certainty of finding something, it has no information whatsoever. Let me make another example. Suppose that you have a language, okay, in which there is only one letter, E, let's say. And when I talk, I say E. Do you understand? Am I communicating any information with this? No, right? But if you have a language with many letters or many different words, depending on the probability of, I don't know, saying yes or no, right? For my kids, it's important, the probability of getting a yes or a no. Then you get some certain information. All right, so all of this to say that the amount of information that is contained in a string or in whatever depends also on the probability of it to occur. If you have an event that is certain, if you have a probability distribution in which you have one event that is certain and all other events never occur, there is no information whatsoever in the probability distribution. Okay? So as you have seen from this example of the yellow light and the red light and so on and so forth. So, this said, so this is 9th. We understand, therefore, that we need something mathematical to characterize the information that is contained in a probability distribution, because, you know, we understand that a probability distribution contains this information. So, this something should be such that the information, let's call it I, of Pn equal 1 of a certain event should be equal to 0, right? So if you see only yellow, there is no information whatsoever in that event. So this should be equal to 0. Moreover, well, we want the information to be positive, right? And we also want the information to be additive. In other words, if I have two events occurring in a sequence, this and that, I want the information to add up, okay? In other words, if I have I of P of N and M, okay, of the sequence N and M, this should be equal to, which is equal, as we know from the law of composition of probabilities, Pn times Pm, this should be equal to I of Pn plus I of Pm. All right? This is another natural requirement for the information contained in a certain event. Right? Okay, so now, what is the function, the mathematical function, which is such that this function evaluated on 1 is equal to 0? And if you take the logarithm, and the function evaluated on a product is the sum of the function evaluated on the two terms, it's a logarithm, exactly. So all these requirements imply that my information Pn should be equal to some constant that I cannot fix. So let's call it, how did I call it here? A times the log of Pn. Now, the constant A is completely arbitrary, right? And the base of the logarithm is also arbitrary at this moment. So I cannot fix it. There's no way I can fix it. I'm just trying to characterize what is information in general terms. So how do I proceed now? Well, so let me describe how people operate in different contexts. For example, in computer theory or in general information theory, typically the base of the log is chosen to be equal to 2, and the constant a is chosen to be equal to 1. Okay, so let's put a base here, such a way as to erase this. B equal to 2, A equal to 1 in information theory. So what does this mean? This means, for example, that if I have a dice, right, that has a coin that has two possible configurations, head and tails, and I have P of head equal to P of tails equal to 1/2, right? Then what I have is that the information of head, of P head, is equal to the information of P tails is equal to 1. Okay? Because it's minus log of base 2 of 1/2, which is log of base 2 of 2, which is 1. Okay? So this is also known as 1 bit of information in this context. And all your computers and cell phones operate by combinations of bits of classical information in this sense. I mean, bits are up or down, 0 or 1, whatever, but two possible configurations for each bit. All right, now, if I now have, for example, so this is in information theory, in statistical mechanics, B is equal to E, to the Kepler number, and A is actually a dimensionful number, is equal to the Boltzmann constant, K Boltzmann. All right? This is because the entropy has a certain role in thermodynamics that we will see. But essentially, this is how it occurs in statistical mechanics. We will see this, so don't be upset if you've never seen it, but the important thing is these are essentially two faces of the same coin, and the coin is the concept of entropy in information theory or in probability theory, which is just the information content of a certain probability distribution. So now, what is entropy? Entropy is the average information content of a distribution Pn. Okay? So, what is the average information content? I will have to solve it. The entropy is usually called N. This would be I Pn. And this would be equal to minus minus A sum over N Pn log of Pn. So this is the definition of entropy in probability theory, right? It's the average content of information. Information is the log of Pn, and therefore if I have to take an average, I multiply by Pn and I take a sum. So, for example, what is the entropy of a dice? When you throw dice, what is its entropy? Let's say we take the information theoretical version of entropy. So we set A equal 1. We set the log in base 2. So what is the entropy of throwing a dice? Anyone that can do it fast?
It's like minus logarithm of 1/2.
Of 1/2? Why 1/2?
Because the probability for the dice heads or tails is 1/2.
No, and that's a coin. It's
Oh.
not a dice.
Oh, sorry.
Minus logarithm is
1 over 6.
So which is log of 6,
Yes.
right? So it's equal to log of 6. Dice is equal to log base 2 of 6, which is something slightly larger than 2, right? It's 2.5 roughly. So the entropy of a dice, information entropy of a dice is 2.58 bits. All right. Now, what is the probability distribution if I have a dice, for example? What is the probability distribution that maximizes the entropy?
all states are equally likely.
All states are equally probable, which is hopefully what happens when you throw a dice, right? Otherwise, one of us has been cheating, right? So if I have n events, n belonging to 1, n, then the probability distribution P of n that maximizes the entropy is the one which is in which every event is equally probable, okay, for all. So this one maximizes the entropy. So how to prove this? For example, let us do it for, this is not going to be a mathematical proof, it's going to be a physicist proof. So I'm going to do it for a coin, and then the rest you do it at home. So suppose that I have a coin, and I have the probability of, head equal to 1/2 minus delta, the probability of tail equal to 1/2 plus delta. And now I look at the entropy S, which is equal to minus 1/2 minus delta log of 1/2 minus delta minus 1/2 plus delta log of 1/2 plus delta. And now what do? I just expand in powers of delta and see what comes out for small delta. And what I will get is that this is log of 2 minus 6 times delta squared. Well, strictly speaking, this proof tells me that this is a local maximum. Then if you plot this function as a function of delta, you will see that it's also a global maximum, okay? So, but quickly you will see that this is a local maximum at delta equal to 0. Now, if you're looking for the precise proof, I'm sure that in any book on probability theory, page 2, or information theory, you can find the proof of this. Now, there's also something else that is very important about the entropies. Not only that the uniform distribution maximizes the entropy, but also the fact that if I have two uncorrelated events, N and M, which are uncorrelated, okay, then the entropy is additive. Right? Now this is important because if I have two, if I'm traveling on a road and I have two traffic lights and the first one is yellow blinking and the second one is normal, then of course the only information I see is the information of the second traffic light. The first one doesn't give me any information, right? But I want to sum them up, not to multiply, because if I would multiply, I would get 0, right? Because the first one has 0 information. So also the average information is going to operate in the same way. So how do I prove this? It's actually quite simple. So S of P, N, and M is equal to S of Pn times Pn. Now, what is this? This is minus sum over N and M of Pn, Pm log of Pn, Pn. Now I use the composition, the rule for the logs, sum over N and then Pn, Pm log of Pn plus log of Pm. And now this is equal to, is equal to minus sum over M Pm times sum over N Pn log of Pn minus sum over N Pn sum over M Pm log of Pm. But now sum over M Pm is equal to 1 by definition. So this is equal to 1. This one is also equal to 1. And therefore I get that this is equal to minus these two things, which is S of Pn plus S of Pm. Okay? So this is clear and obvious. Good. So now that we are done with the theory of probability, with the entropy, because I have nothing else to tell you about entropy, to be honest. I hope you understood what it is. Any question? No. So now I wanted to do with you, before starting with thermodynamics, I wanted to do one exercise of the theory of probability, which I find very useful because it's also inspired by physics. And this exercise is the solution, if you want, of what is known as a random walk. Have you ever heard of this name, random walk? All right, so what is a random walk? I have a lattice. Let's say I have a one-dimensional lattice to simplify my life. So I have a one-dimensional lattice like this one. And I have a discrete time. Okay, and at every time in my discrete sequence, I have a certain probability to hop on the left or to hop on the right. Okay? And the probability to hop on the left is, let's call it Q, the probability to hop on the right, we call it P. P can be equal to Q or P can be different, it doesn't really matter for me at the moment. The only important thing is that P plus Q is equal to 1. Okay, I have a normalization. Now, I can write down this formally by saying that at each instant of time, I have a probability of performing a jump of sigma, of size sigma, which is P times delta sigma plus 1, of moving to the right, plus Q delta of sigma minus 1. Okay? And now, what I'm interested in is the probability of finding out what is the probability of distribution of my position after n, big N, such steps. My position after n steps. So formally, I write down this position as x equal to sum over j from 1 to n of sigma j. Okay? This is formally what it is. So let me now start asking the following question. Suppose that I'm not really interested in figuring out what is the probability distribution. We'll calculate the probability distribution, but for the moment, forget it. So I want to know what is the average, okay, position I will have after n steps. So how do I calculate it? I should be able to do it quickly.
You take the position and multiply it by the probability.
You take?
The position of the n steps and then multiply it by the probability.
What do you mean?
X times p.
X times p. What is x? That one? No, but this is a random. This is a random variable, right? It's a sum of random variables, of independent random variables. So after n steps, what is going to be the average position? It's a sum of independent, equally distributed random variables. So after n steps, what is going to be the position? What is going to be the average position? It's the sum of n equally distributed, independent random variables.
No.
Independent.
The average of x
Yes, the average of x
is the sum of average of sigma j's.
Well, good, correct. So it's the sum of average of sigma j's.
The average of sigma j has to be the same for every.
It's all the same.
All the same.
And
So
is
it's-
equal to what?
It's n times average of sigma, and the average of sigma can be calculated from the
Which is equal to
p for the left, q for the right. It has to be p plus q over no
p minus
p
q.
minus q.
Okay, so it's n times p minus q.
Yeah.
Okay? It's n times p minus q. So this is the average. Okay? What about the x squared, average of x squared? Okay? So this is slightly more complicated. So you need to, we'll do it together, but pick paper and pencil. So this is equal to sum over I and j from 1 to n of sigma I times sigma j. Okay? Now, let me distinguish now two terms in this sum. The first one is when I is equal to j. Okay, so let me write it as sum over I from 1 to n of sigma I squared plus sum over I not equal to j to n sigma I sigma j. Okay? Now the reason I'm distinguishing them is because if I take sigma I squared, sigma can be equal to plus or minus 1, and therefore this is equal always to 1, right? And therefore this object here is equal to what?
Is something always positive?
Sorry?
Positive number?
It is a positive number, certainly.
P squared minus.
No, not p squared. I just said sigma I is always equal to 1, right? So what is the average of 1?
Yeah, it's n.
Is n, right? Because the average of 1 is 1.
The first term is describing the probability of just hopping, which is
Just hopping,
yeah.
exactly, that's correct. So, right, sigma I is always equal to 1. Is sigma I squared, sorry, is always equal to 1. The average of 1 is 1, right? Because it's P plus Q, which is equal to 1 by definition. You see? And therefore, this is equal to n. It's just as he said it correctly. It's the probability of just hopping. Doesn't matter where you go. So this is equal to n plus. Now we have to be careful. I is certainly not equal to j, but so different events are how are they? They are. I said it, independent, right? So therefore this is equal to sum over I not equal to j to n of, if they are independent, this is the average of sigma I is the product of the averages, right? If I have two independent events, the average of the product is the product of the average. Is that clear to everybody? Okay. So, therefore, this is equal to what? To n plus the average of the product of the averages, which is sum over I not equal to j up to n of p minus q squared. Correct? Because the average of sigma I was p minus q. Is it? Are you all with me? Now, how many terms are, now all of these terms have the same, give the same contributions. How many terms do I have in this sum? N minus 1? Not really. How many terms? Now, the reason I'm doing this exercise with you is because it's the first exercise that you see that might be similar to something you will find in the final exam. Okay, so you see how they look like.
Is it NC2?
Is it
NC2?
NC2?
Yeah, combination?
No.
P and Q is
N squared minus n. Correct. N squared minus n is the correct answer. Why? Because if I would not have the restriction of I not being equal to j, how many terms would I have in this sum? N squared, right? But since I don't want I to be equal to j, I have to subtract n, right? And therefore this is equal to n plus n squared minus n times p minus q squared. Okay? Now suppose that I calculate x squared minus average of x squared. What will I get? I will get n plus n squared minus n p minus q, right, squared, minus average of n squared, right? Now, average of n squared is what? Is n squared times p minus q squared. And therefore, if I now take these terms, add, subtract, do whatever I want, you see easily that the two terms with n squared, this one and this one, cancel each other. I get only terms that are proportional to n. This is very important. And, most importantly, I will get at the end 4 times n times p times q. Okay? So this is the final result. You do the algebra. I hope it's correct. All right. So now, I know what is the average of this distribution. I know this. Question. Suppose that n is large. What is the distribution? It's a Gaussian, right? It's a Gaussian. You see, the important thing of this, of what I told you last time, the central limit theorem, is that if I have a process which is the sum of independent, if I have a variable which is the sum of independent variables, and I know how to calculate the average for each one of these independent variables and the fluctuations, then I don't even need to think about what is the distribution. I can just write it down. I do these two calculations and write it up. In particular, what I will find is that in the limit of n much larger than 1, which is a way to say n is super large, then my probability distribution Pn of big X is going to be equal to 1 over the square root of 8 pi n times pq times the exponential of minus x minus n times p minus q squared divided by 8 times n pq. Okay? So this is my distribution. This is how it should look like. Now, one thing we might be interested in now is to check ourselves for this simple example, which is exactly solvable, a random walk. I mean, this random walk in one dimension is a straightforward exercise, to check whether it's indeed true that in the limit of large n, this is what you get. Okay? So this is the next thing we're going to do. We're going to solve exactly the problem, then take the limit of large n and check that for this variable x, this is what we get for the distribution from the exact solution. So how do we do it? Right, so if I want to solve exactly for Pn of x, and x is equal to sum over j from 1 to n sigma j, then what do I have? I have that I can think of this variable x as being equal to the number of steps that I perform to the right minus the number of steps that I perform to the left, right? Because each step has size 1. Do you agree? No. Do you agree?
Yeah, this is the width of one step.
No, the width, so the one step size is 1. So every time I move of 1 to the right or of 1 to the left. If I move n times and I want to know where I am, it's enough that I tell you I moved nr times to the right and nl times to the left. It's not important in which sequence you move. because it doesn't really matter. If I move, let me make an example. If I move twice to the right and once to the left, it's the same as if I move once to the right, then once to the left, and then once to the right. The final outcome is the same, does not depend on the sequence. What is important is just the number of steps that you perform on one side or on the other side. And the other thing I know is that n is equal to n right plus n left. Now, if I know these two things, then the question that I have, if I want to find what is x, is the following. How many ways, given n total number of something, how many ways I have to select nr steps to the right and nl steps to the left such that nr plus nl is equal to 1. Not only how many ways I can select them, but then what is the probability of performing this. So let us first solve the problem in combinatorics. How many ways do I have to select nr to the left and nl to the right? Correct. So the number of configurations, number of ways, is going to be n factorial divided by nr factorial times nl factorial. Okay? And then if I want to find what is the probability of having this x, what I have to do is I multiply the number of ways I can get this configuration. So I multiply n factorial times nr factorial and L factorial, and then I multiply this by the probability of performing n steps to the right and nl steps to the left. And this probability is nothing but p to the power nr times q to the power nl. And this is my exact solution. Full stop, right? Now you can tell me this is written up in terms of left and right. How do I write it in terms of x?
Just use the number of...
I just use the number of particles and x, and you see that if I use these two equations, I can rewrite nr as being equal to n minus x divided by 2, and nl equal to n plus x divided by 2, yes, and minus x divided by 2. Okay? So I reparameterize everything and I write everything as n factorial divided by n minus x divided by 2 factorial, n plus x divided by 2 factorial, and then I have p to the power n plus x divided by 2 and q to the power n minus x divided by 2. Okay? So we agree with this. Great. So this said, then now I want to know what happens to this probability distribution when n is very large. Okay? So the way to obtain this limit is to take the log of this probability distribution p of n of x. Now this log is equal to the log of n factorial minus the log of n plus x over 2 factorial minus the log of n minus x over 2 factorial, and then plus n plus x over 2 log of p plus n minus x over 2 log of q Okay? Now, what do I do with this? Stirling. I see that everybody, this is my experience. Entropy is a mystery. Thermodynamics is a disaster, but Stirling everybody loves and knows, right? Stirling is, so log of n factorial is n log n minus n, right? For large n. So now I use systematically this. I do some algebra. Well, let's do it slowly. Otherwise, it might end up in a disaster, at least for me. I get log of p and x equal to what? Equal to n log n. Sorry. N log n minus n plus x over 2 log of n plus x over 2 minus n minus x over 2 log of n minus x over 2. And then I will have the other two terms which are always the same. So n plus x over 2 log of p plus n minus x over 2 log of q. Now I do the following. I introduce a variable which I call little x equal to big X over n, and I rewrite everything in terms of this little x. This is equivalent to essentially taking out an n here, 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 right in front of everything. So what will I get? I will get that if I take out n, I will get minus n times 1 plus x divided by 2 log of 1 plus x divided by 2 plus 1 minus x divided by 2 log of 1 minus x divided by 2 minus, I need to go to the other side, I'm sorry. So whoever is copying, copy now or not copy forever. So minus 1 plus x divided by 2 log of p minus 1 minus x divided by 2 log of q. Okay? So I can rewrite this as minus n times a certain function of x. Okay? So the function of x is simply given by this. Well, let me rewrite it just to have it. Plus 1 minus x divided by 2 minus 1 plus x divided by 2 log p minus 1 minus x. So this is my function f of x, okay? Where x varies between 0 and 1, okay? Now, this writing implies that my probability distribution p of little x, which is big X divided by n, is going to be equal to a certain constant c times e to the minus n f of x, right? Now, this is the exponential of a function, which is positive, right? And multiplied by n, where n is super huge, is very, very large. Now, when you have an object like this, you can easily imagine that this function is going to be strongly peaked around the minimum of f of x, right? Because if I have a minimum of f of x, let's draw it. So if f of x looks like this, it has a minimum. So the corresponding function is going to have a certain value. The corresponding function e to the minus n f of x is going to have a certain function, a certain value here. I don't know what it is. But then as I slightly vary my f from this point, the decrease is going to be exponentially fast because it's multiplied by n, and n is very, very large. Okay? So in practice then, this means that if I want to figure out what is a good approximation for this distribution here, I can just find what is the minimum of this function and do an expansion around the minimum. And this will approximate essentially most of my distribution. Okay, is it clear? Because it's all of this is the basis of what we will call later on in this course the saddle point method to estimate integrals. But, essentially it's also central limit theorem. All this stuff is the same stuff. Good. So now let us erase this ugly figure and let us find the minimum of this function. What is the minimum of f of x? Well, in order to do it, I take the derivative f prime of x, which is equal to 1/2, if you do it, 1/2 log of q over p times 1 minus x times 1 plus x, 1 minus x. So this should be equal to 0, right? Which implies that the argument of the log should be equal to 1. And therefore I have that 1 plus x divided by 1 minus x should be equal to p over q. And this means that the value for which I have a minimum, x bar, is equal, if you solve this equation, to p minus q. Okay? Which is, by the way, the average. So it's not surprising. The function f is peaked around the average of x, little x. Now, the other thing we can do is take a second derivative of x, which is equal to 1 over 1 minus x bar squared, and this comes out, if you do all the calculation, to be 1 over 4 times p times q. Now this implies, therefore, that if I take my f of x and do a Taylor expansion around x bar, I will get f of x bar plus f double prime of x bar times x minus x bar squared divided by 2. Now f of x bar turns out to be equal to 0. Okay? If you do, if you put in the numbers. Sorry, but I have to check one thing. Okay. Is equal to 0, and therefore, if I now take p of n of x and write it as e to the minus n f of x, and put the Taylor expansion in here, I will get only the second order term. So this is approximately c times e to the minus n f double prime x bar divided by 2 times x minus x bar. squared. So this is equal to c times e to the minus n x minus p minus q squared divided by 8 times p times q. Now, if you now pass back to the variable big X, which is equivalent to taking this n and putting it in there, you will get that this is equal to a constant times e to the minus big X minus n times p minus q squared divided by 8 n p q. Okay, so exactly as the one we got before. So this is the central limit theorem that I explained last time in practice. Okay, and you see that it's essentially coming because when n is very, very large, your distribution is essentially strongly peaked around the average and exponentially decaying on the two sides. And therefore, only the lowest order term in the Taylor expansion of the exponent matters. So that's how the central limit theorem comes out. All right? Good. So how do you fix C? You fix C here by normalization. Normalization. Good. So, I think we are done with probability theory.
Sorry.
Yes.
Question. When we, from the beginning, we had two capital, like quantities, capital X and capital N.
Yes.
Are they of the same order? Because when we write the small x, which is the like capital X, or
that's
capital
a good,
N, like,
that's a good point.
Can we Taylor expand on those logarithms?
No, so the point is the following, that so we are assuming, I mean, in practice, what you're assuming is that your process is such that, I mean, your distributions are going to be centered. I mean, the essential, where you're going to do the expansion is around
Small x.
is that, I mean, n minus x is going to be a finite number. You're never going to reach configurations in which x is equal to n or x is equal to,
Yeah, of course.
to minus n. That would happen if you have a trivial random process in which you always move to the right,
Yes.
or you always move to the left, right? But what we are disregarding that opportunity. So I was actually almost going to say it, and then I said, let's not confuse them even further. But of course, when I do expansions here, I'm always assuming that x is not of order n. So it's something smaller than n. So I cannot have a configuration. The weight of configurations in which n is equal to x is small.
Small.
Yeah.
So at some point we could just Taylor expand it in terms of small x, like this logarithm of Pn. Could we? Or
Which one?
like on the next page when we have this f function with small x.
This one? This one?
Yeah. Yes, the green one.
Yes.
Yeah. Maybe we could expand it in terms of small x.
Yeah, that's what I'm doing. That's what I've been doing here, right? I've been doing the Taylor expansion. I found the minimum by solving this equation. I did the Taylor expansion.
Without finding the minimum, like
Well,
assuming that x is.
you always have to expound around something, right? I mean, you can. The problem of expanding not around the minimum, I'll tell you what it is. The problem of not expanding around the minimum is that you will get also first order terms here that go as x minus x, right?
Yes.
And moreover, it doesn't make much sense because this function is going to be strongly peaked around the minimum, so you essentially want to study only small deviations around the minimum, which are the ones that are going to matter. So in a sense, you're right. I can do a Taylor expansion. That's what I'm doing. I'm doing it around a
Around the
certain
minimum, okay.
point, which is the minimum of the function. Okay? Any other question? Comments, complaints, requests? No. Okay, so let's go on. We still have half an hour. So. All right. So, all right. So now we start with the probably painful part of the course for you, which is the one about thermodynamics. But it's important to lay down all the rules of thermodynamics because essentially, you know, the story of statistical mechanics is just a way, as I explained already in the first lecture, is just a way to derive thermodynamics from scratch, from Newton equations and Schrödinger equations. So what is thermodynamics? Thermodynamics is actually it's actually a very general theory. It's so general that I read recently that Einstein believed that unlike other physical theories, it will never be overturned, right? It's not like you know, Galileo theory of relativity or any other thing that eventually in some limit it's wrong. Einstein believed that thermodynamics is always true. I mean, it's always so general that it cannot be wrong. There are some caveats. It's not entirely true what he thought. But it's a theory that was invented actually with a practical goal in mind. So think about, let's make a trip back in time and go back to the 19th century when people were starting experimenting with electricity, with vapor, with gases and things of this type. And back then, so they didn't really have all the concepts we have about energy and various forms of energy and so on and so forth. But they noticed that there are certain forms of energy that are much more useful than others, right? For example, you can use steam, the heat of steam to perform a certain work on engines, but a lot of this energy is wasted actually in dissipation. And so they were interested in classifying various forms of energy and figuring out what are the general rules with which energy transforms, and that's it, essentially. So some very general principles, with a practical goal in mind that was to drive the Industrial Revolution in England, essentially, and in France. Partly in Italy, but not that much back then. All right, so the first thing we have to realize when we talk about thermodynamics is that, you're used to think about I was used to think when I was a student about thermodynamics as a theory about, the static states of matter, equilibrium states of matter. This is incorrect. Thermodynamics is a theory that characterizes transformations between different states of matter, okay? And characterizes transformations in terms of some very general variables. Variables that are so general that you can measure them. You measure them every day in your life. I'm not sure that, I don't know if you make pasta, but when you make pasta, you're using thermodynamics. And also when you make coffee, you're using thermodynamics. If you use a mocha. You know what is a mocha? You've never seen this coffee machine? You've never seen it? Do you have it at home?
Yeah.
It's called mocha. Do you know how it works? Do you ever make coffee with a mocha? No. Oh, guys. Now, it's extremely important for this course that you learn how to make coffee with a mocha. Okay? Because when we will talk about phase transitions, actually, we will be discussing making coffee with a mocha and how the mocha operates. It's going to be one of our examples. So, let me very quickly tell you how to make coffee with a mocha, but let's stop.